Hello, everyone. Uh, hello. I, uh, hello, everyone. Are you seeing my screen? Okay. Okay. So today we're going to discuss with you the past exam of Journal Physics 1. This is all about solving problems and past exam. So this session will be on the past exam, which will happen on 17th of October 2024. So it's a midterm exam. So we're going to solve it. Please, those who are unmuted, mute yourself. And if you have any question, you can ask by unmuting yourself while I am teaching or while I am discussing the problems. This session will be recorded, and the recording will be available to you as well. So let us start. So this is the exam, General Physics 2, a midterm exam, and you will contain a similar kind of problem set and all that stuff over the here. So the first problem will be the MCQs problem. Then you have a problem set, problem 2, then problem 3, and then problem 4. So admit all. Okay. So the most important thing is that what you have learned in your class is is how to is how you can reproduce in the in exam. Hello. Please unmute yourself. Please mute yourself. All those who are there. I'm hearing some sound. Okay. So the first thing you learned is the charge force, which is force is K Q1 Q2 over R square. It's Coulomb's law. And then you learn that is force is QE, and E is force over. Then you learn for the electric field of a point charge is nothing but KQ over R square. The potential for a point charge is KQ over R. And then you learn the electric flux, which is nothing but E dot A, or you can write flux in terms of the integral E dot dA closed surface. And this is what you have, the Gauss law, the electric flux. And this electric flux is the charge enclosed divided by the epsilon naught. And then you have the potential energy, which is q dot v naught, or work done is qv, or v is your potential. So these are the thing that we going to use. So the first thing we learned that the like charges repel each other and unlike charges attract each other. Hello, Suleiman, just mute yourself. Okay, so the most important thing that you have these formulas and there is a physics involved in it. So this is force, and the force between two charges, and there is a thing distance. If you increase the distance, force will go down, and if you increase the charge, force will increase. So this is no, and this k is constant, which is depend upon the medium, which is 4 pi epsilon naught, and this constant is given this number. This is epsilon naught, relative permittivity of free space. This is the mass of the proton, because many of the questions, proton and electron, you have the mass, and you have the mass of the electron over here. Then you have this charge of the electron, and this is g, gravitational acceleration. So these are the constant that is going to be part of your exam, as this is the mass of the proton, that's mass of the neutron. And if you have a question in H which is having proton and neutron, use this mass, use this charge. For the electron charge, you use negative, and for the proton charge, you use positive 1.6 10 to the power minus 19 coulomb. Okay, there are some prefixes that mostly used in the electricity and magnetism course, which is 10 raised to power minus 6 is equals to micro, 10 raised to power minus 12, which is pico, 10 raised to power minus 9 is nano. Okay, so these are the prefixes that is frequently used. So force has a unit Newton. Newton. So charge has a unit coulomb. Electric field has a unit Newton Newton per coulomb, and the potential has a unit volt, or or joule per coulomb. Okay, and the energy, or the potential energy, or electric potential energy, or the work done, measured in joules. So these are the units that we going to be express our answer in terms of it. Let me add the participant. People are coming.
Doctor, did you make screen record?
Yeah. Yeah, I am recording it. Yeah, this is recording. Okay, so now let's move to the next first question. So their first question is all about MCQs. You need to answer an option. So let's understand the problem first, and then we will move on. So the first question is says that in order to avoid the impact of a positive ions falling on the surface, it is proposed that to deposit a charge on the surface. What must be the sign of the charge on the surface of the to push ions away from it? So if the positive charge is coming, which option is this? If we take it to what charge we separate on this spread on this sheet, so it will avoid or stop the charges from coming. So I told you like charge is positive, positive repel, and negative, positive attract. So if we don't want the charge to be on the surface of this sheet, these positive charge to be deposited on the surface of the sheet, we want to stop it, we make it positive. If we want to deposit these charge, we make it negative. So in that case, what must be the sign of the charge on this surface? To push. To push means to go away from this, the ions away from this. So the answer is the surface must be positively charged. Okay, now next question is choose the correct figure that the electric field lines about the 2 point charges plus q and minus 3q, which are represented at distance. So if you know that the electric field originate from the positive charge and terminate on the negative charge, originate from the positive charge and terminate on the negative charge. So the field lines of a positive charge would be like this, and the field lines for a negative charge would be inward, source or sink concept. Okay, so if you see the diagram, okay, first see this diagram A. So diagram A is positive charge and the field is emerging. So this is correct. So a negative charge, the field is this. So positive to negative. So this seems a correct option. Next C. So if you have this, a positive charge. So lines originate from here and terminate over here. But you see the arrow over here. That is not correct. It means this is not the option. So let's see the option 3. The positive is going here. Okay. And the negative is going over here. But if you see the amount of magnitude of the charge, it's q and 3q. So the lines of 3q has to be more as compared to the lines of the plus q. So this could not be an option. So what about this option?
أقولك بوقف الفيديو.
Hello.
كلمة.
Okay, so now move to the next question, next part. If you see these are two. So if we have one option and one option here, if you see this is 3q and it is inward. So this is the correct description as well. And this is the correct description as well. So what if you think this is 3q and the lines are very only few lines. So this is not the field of 3q. So because and so this is the correct option. Why? Because for 3q more lines has to be there and for q few lines has to be there, and the lines should originate from positive charge to end at negative charge. So this is the correct option. So in the question 2 case, the correct option is 2. So you need to identify the magnitude of the charge and in what direction it is going. The charge field lines always grow from positive to negative. If you have 5q, you have more lines. If you have 5q, you have more lines. If you have 1q, you have less lines. So you have to identify what is the magnitude and in which direction it's going to predict these kind of questions. This is field line question. Now let's move to the next question. So an electric dipole is in a uniform electric field in such a way that the dipole the dipole moment P is at an angle theta, which is electric field as shown in the figure. How does the potential energy of the dipole changes if the rotate clockwise? If it rotate clockwise in that direction. So if the dipole rotate anti-clockwise, the angle is positive, and if the dipole is in this direction, the angle is negative. So because it contains sine of theta, so sine of negative theta will give you minus. So the energy will decrease in that case. So in that case, energy will decrease. Now, the next part is question number 4. A plane surface in a uniform electric field with different values for an angle theta between the normal n to the surface and the electric field E. Rank the greatest to the least. Greatest to the least in an algebraic values, the flux. So if you know the flux is nothing but E dot A, E dot A, and unit vector En. For example, n is a unit vector Ea, and so it has En or A cosine theta. So cosine theta. So theta now it depends theta on the theta. So for cos theta, if angle is 0, then it has a maximum value. If the angle is 90, then it is 0. And if the angle is 180 degree, it is minus 1. So this is the maximum value on the positive side. This is the maximum value of the negative side. And if the angle is 90, like if the electric field and electric normal vector are perpendicular to each other, then 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 it has to be 0. So if you point out in which direction, in which the normal angle is 90. So if you see these three diagrams, we see that this is 90 degree. It means this is the least one. Why at least one? Because its flux is 0. Because the electric field is in this direction and it is the normal direction is this. Okay. Then then you have this. Okay, then you have this and this angle. This is more than 90 degree if you see this, and this is tilted as well, and this is tilted as well. So the flux which is in this case, which is closer to the field lines because it is near to parallel, near to 0, is greater, and then this, and then this angle. Okay, but if you see this angle, so cos this has to be like 120 degree, which is the negative value. So this is 0 and this is positive value. So you have a flux in this condition maximum, then this, and then this. So the flux of phi of C is the greatest. Then you have a flux of B, and then you have a flux of A. So the correct option in these situation is the flux of A is greater, the flux of B is then, and then flux of A, because greatest to least. So C to A. So the correct option is over here. Mm, C. Yeah. So the correct option is C because C has a greatest. If how to check this question, if you have a similar question, if the angle between them is the least, the electric field and the normal is least, then you identify has a maximum capacity of the flux, because if it is closer to zero, then it has a maximum value, cause has a maximum value. If it has perpendicular to each other, then the flux is zero. And if the angle is more than 90 degree, then cos goes to negative value. So this is the correct option. So if you get a similar kind of question, identify the vectors, the electric field vector and normal vector. If they are close to each other, then it has a maximum flux, and if they are perpendicular, then zero, and so forth. Okay, or at least identify these options as well, greatest to least. He can ask you least to greatest. Least to greatest means this is the least, then this, and then this. So if the question is reversed, then you need to answer like that. Now moving to the question number 5. A point P inside a very thin spherical shell. A point P inside a very thin spherical shell of radius r. The spherical shell is uniformly charged with the surface density of the charge. The point P inside the at a distance r from the center of the spherical charge, see figure. What is the electric potential by a charge? I have told you the electric potential for a charge, for a point charge, is nothing but V is equals to KQ over R. So in that option, this is not the case because it has a charge. This is not the case because it is squared. And now this and this option, because they both have R. So at what point they want us to calculate what is the electric potential created by the charge Q, this charge on at point P. Okay, so this charge is related to the distance this, and at this charge is related to the this distance. So if we are talking about this charge, this is the correct option. And if you are talking about this charge, this is the correct option. So he is talking about the charge Q inside it. So charge Q is this. So the correct option is B in that case. Because the electric potential of a point charge varies as 1 over R. If you increase R, the potential will decrease. And if you increase Q, the potential also increase in that case. Now move to the next question. Now you have 5 questions of MCQs, and then you have a question like the problems. So for that, you need to remember these formulas. So if it is not given into your exam, you need to memorize it. This is what you have for the midterm exam. So let's see what's the problem is. So the first problem is that two identical positive point charge, Q1 and Q2, 4 nanocoulomb, are located respectively on x-axis. At x1 is 3 centimeter, and at y-axis y2a is 3 centimeter. So one charge is on y-axis and one charge on the x-axis. Third point charge Q3 is negative 12 nanocoulomb, is located at x equals to 3 centimeter and y equals to 3 centimeter. So this is the location of the charge. This is same. So every option A, B, C, D had different point scheme. So the first question starts from the draw the vectors of the three electric field E1, E2, and E3 created by the three charges. So this is a positive charge. So if the electric field originate from the positive charge, so it has this direction. So at this point, this is our origin, and we are seeing everything from here. So what is at this point, this charge is giving its electric field. So electric field of this charge should be in this direction. So this is your E2. This is a positive charge. So it also repelled by a point charge. So its electric field should also originate from here, and it has to be in this direction. So this is the electric field of E1. Now, what about 3? 3 is negative charge. So it starts from the positive charge and terminate at the negative end. So its field has to be inward. So the electric field of third charge should be represented like this. So this is E3 at this point O. Okay, so at this point O. So this is E1, this is E2, and this is E3. So in your exam, if you do this question, you get 3 points. Now, find the magnitude and directions of the total electric field. Total electric field created by these 3 charges at O. So now there is a superposition principle applied. So what is superposition principle says that? It says that to calculate the electric field for sum of all charges is just adding their separate electric field. Okay, so this is a very powerful superposition statement. It says that if you are calculating electric field from the bunch of charges, you need to calculate the electric field of a first charge, then electric field of a second charge, and then electric field of a third charge to calculate the total electric field. So in that case, we have 3 charges. So we have to calculate electric field of every charge with this. So if you see this, this first charge is on x-axis. So it has only the x component, and its y component is 0. If you see this charge, the Q2, then then it has only the y component, and its x component is 0. So its x component is 0. But if you see this third charge, is both x and y components are there. So it's making an angle theta with the x-axis. So it both has 2 components, x component and a y component. So what is the electric field due to this point charge? So I've told you the formula. Let me add the people who are coming. Okay. Okay, admit all. Okay, so the electric field due to a point charge is this. So this is the electric field due to a point charge. E is equals to k q over r square. So we have a charge q and we have a distance a. They are a apart. So we can calculate the electric field. So what is the electric field for E1 is nothing but K Q over R square. And R is the distance between the origin and the charge. Okay. Now, so what is the total electric field? So K is 9 into 10 is power 9. This is given in your constants. Then what is the charge Q1? So Q1 is 4 nanocoulomb, which is 4 nano is 10 to the power minus 12 divided by the R. R is the distance between this distance, origin and the charge, which is A. So what is A?
Not minus to power minus 9.
Nano, yeah, sorry. Nano is 10 to the power 9. Yeah, I was thinking as pico. Very good. Thank you. So the x distance is 3 centimeters. So 3 centimeters means 3 into 10 to the power minus 2 meters square. So the electric field, if we calculate, is 4.0 10 raised to power 4 Newton per coulomb. So this is the electric field total. But what is the electric field x component? So the charge is along the x. So this is your electric field along the x. But its direction is in this direction. So if you have this uh, origin and this is the positive x and this is the negative x, so your electric field direction in the negative x direction. And what is its y component? Is 0. Similarly, we can figure out the electric field of a charge too, which is k q over r2 square. This is r1 square. So k q over r2 square is the same because they have the same charge. This is the electric field for 2. And what is its electric field? X component is 0 and it's only in the y direction, which is negative 4, because if you see, this is your positive y and the electric field is in this direction. So this is negative y. So negative y means you have to show the negative signs because its electric field is a vector quantity. Now, what is the electric field E3 of a charge? So it's K Q3 over R3 squared. But we don't know what is this R3. So if you see this, this is becoming a right angle triangle. This is becoming a right angle. So this is A. So this becoming a right angle triangle. This is A. This distance is A. This distance is A as well. So this distance is A. This distance is A as well. So we can find the hypotenuse, which is nothing but using the Pythagoras theorem. So we will get R3 just by getting A square plus A square, because the base square, the perpendicular square, is equals to the hypotenuse square, which is A square is B square plus C square. Simple Pythagoras theorem. So we have A square and A square, and then we will get we will get A square root 2, which is nothing but 3.0 square root 2 centimeters. And when we substitute this value into this equation, we we will get E3 is K Q3 over 3.0 square root 2 whole square centimeter, and we can convert into meters just multiplying it by 10 raised to power minus 2 meters. So when we calculate the field of electric field, we get 0.06.0 10 raised to power 4 Newton per coulomb. So now we have we have the electric field E1, we have the electric field E2, and we have the electric field E3. Now, if you see, this electric field has both components of X and Y. So what is the X component of this E3? So E3 X component is nothing but E3 cosine theta and E3 Y E3 sine theta. So for the simplicity, because it's a straight line, if you see this is a right angle triangle, this angle is 45-degree because this angle is 90 and this angle is 45 and 45 becomes 90 as well. So we took this theta to 45, then we have 6 into 10 raised to power 4 E3 and cosine of 45-degree. Similarly, 6 into 10 raised to power 4 sine of 45-degree. So we will get the x component of E. X component of E is nothing but 4.243 10 raised to power 4 Newton per coulomb, and E3 is Y is 4.243 10 raised to power 4 Newton per coulomb, because at sine 45 and cos 45 both have the same value. Okay, now we have the all the x components and the y components. So what is the total electric field along x? So total electric field along x is E1x plus E2x plus E3x. And what is the total electric field along EY? So y is E1y plus E2y plus E3y. And we have all the components because E1y is 0 and E1x is this, E2x is 0 and E2y is this, and we have E3x and E3y. So when we calculate these two by putting the values into it, we will get Ex along x is 2.43 10 raised to power 3 Newton per coulomb, and Ey is 2.4, no, so so Ey is the same as well, 2.43 10 raised to power 3 Newton per coulomb. So now we have Ex and Ey. We can now able to have to we can have calculate E, which is nothing but the magnitude of E is Ex squared plus Ey squared. So when we substitute the value over Ex squared, which is this, and Ey, which is this, and square it and then square root, we will able to get our electric field magnitude, which is nothing but 3.43 is 10 raised to power 3 Newton per coulomb. So the magnitude of the electric field is 3.43 3 Newton per coulomb, and it's always be a positive value because magnitude. Now he asks you the question, find the magnitude. So we have find the magnitude. Now how do we find the direction of the total electric field? So direction can be easily found, which is tangent inverse Ey over Ex. This is the theta. So whenever you ask by finding a direction, you have to find by this formula. So will be theta will be tan inverse Ey is 1, and then you will get 45 degree because Ex and Ey has the same value. Okay, so this is how the to structure these kind of problem, you will get a similar kind of problem. Either it can be negative, it can be positive, or it can be positive. So just identify in which direction. For example, if I draw a diagram over here, any another question. For example, you have a charge over here is negative, and over here is positive, and over here is also positive. So you need to identify in which direction the electric field go. For example, this is a negative sign, negative charge. So the electric field of this charge would be in this direction. This is positive, electric field will be in this direction. And this is positive, this is the electric field of the third charge would be. Now, if you see this, this electric field has only Y component, this which is positive, this charge electric field is in this direction, which is negative X. And if you see this diagram, this electric field, this third charge electric field has two components. This is along X and this is along Y, both negative, negative X, negative Y. So you have to count, for example, if we are see this is negative X. So if in this direction, this has to be negative because it's not there or negative because this is a magnitude, but over here is a direction. This is 0. So if you see this diagram, this electric field, so this electric field is positive, but it has to be negative because it was in this direction. So any kind of configuration can be given to you. You just need to identify in that case what you want. You want a total electric field, which is nothing but Ex squared plus Ey squared. So first you have to calculate every X, every Y. Okay, then you have to calculate the total component, which is like this. How many charges are there? Two charges, three charges, four charges. You calculate like this. And then it could be any configuration. It could be like this. For example, you have charges on that. This is positive and this is negative. This positive charge and this is negative charge. So you need to calculate the electric field between them or at this point. So this is positive. This electric field will be in this direction, and this is negative. This field will be in this direction. So if you are seeing from this origin, both have the X component, and this is positive and this is negative. So it could be any kind of configuration given to you. You just have to figure out first their electric vectors and then figure out the magnitude and direction of the total electric field. And this is from how you can find it. So in your exam, this configuration could be changed, but the pattern of the question would be the same. So identify the configuration, which is positive, which is negative, draw their first electric field vectors, and then work accordingly. If you figure out the first part, the rest of the part follows. So the first part is very important in that case. So if you solve this part, which is the B part, you will get 13 points. Next is C. Find the magnitude and direction of the electric force. So electric force, I've given you the formula. Electric force is nothing but the charge time the electric field. So we have the total electric field. We have the electric field, which is this. Total electric field is this. And the charge is given. So we have the formula. We have the formula. So we have the formula. Force is Q E, and Q is 5 nanocoulomb, which is 5 into 10 raised to power minus 9, and E is 3.43 10 raised to power 3. 3.43 10 raised to power 3, and just we will get the force. Force is 1.72 10 raised to power minus 5 Newton, and the magnitude is 1.72 10 raised to power minus 5 Newton. So this is the magnitude of the force. Now what is the direction? If the direction is the same as the electric field. So what is the direction of the electric field? We have calculated. This is the direction at a 45 angle, because the Q is positive. So Q is greater than 0. So F has the same as the same direction of E. So theta is 45 degree. Okay, the next part is D. Calculate the electric potential created by three charges at the origin. And we assume that the potential is 0 at infinity. So how to calculate the electric total potential? Total electric potential similar to this. Similar to this. So what is this? So total potential is nothing but is nothing but so what is this? V1, calculate the electric potential along V1, calculate the electric potential along V2, and calculate the electric potential along V3 of charge V3. So V1, V2, and V3. And potential is a scalar quantity, so we don't have to worry about the direction of it. Just calculate the electric potential due to point charge. So how to calculate electric potential due to point charge? That's the formula. That's the formula. So V is equals to K Q over R. So we have, so we can have it over here. So the potential V1 is nothing but K Q1 over R1. And R1 is nothing but this A distance. This A distance, and we have calculated this distance, which is nothing but A or R is A square plus A square, which is A square root 2. So we have all the distances. So we can now put it into the value. So this is K1, and then we will do K2, R2, and V3 is KQ3 over R3. So this is not square, this is the subscript. Okay, so when we substitute the value into it, we will get the total potential by summing up V1 plus V2 plus V3. So V1 plus V2 plus V3. So calculate these values, and then you will get a total answer, which is negative 145.6 volt. This is not the direction. This is coming from the negative charge, which is V3. So the potential at point O is 145.6 volt. So superposition principle applies as well. in that case, like the electric field, like the potential. And similarly for the forces as well. We can add F1, F2, F3, how many forces are there? This superposition principle is also applied. Okay, now the next part. So what is the work required for an external force to bring the charge Q slowly from infinity to the origin? So how do we find work? It is a potential energy. Work should be stored in terms of the potential energy. So how do we find work? Is by this formula or its potential difference. So we have the formula for the work. So I can do it over here. So work of external, which is nothing but Q delta V. And what is delta V is nothing but V naught minus V of infinity. And we assume that the potential at infinity is zero. We assume that the potential is infinity is zero. So this potential is zero. So we left with Q V naught and we have the value for the V naught. So the is work done is Q and Q is this 5 nanocoulomb. So this Q is plus 5 into 10 to the power minus 9 and the potential is V naught 145.6 with the negative sign V. So we will get the external work done, which is negative 7.28 10 to the minus 7 joule. So if you do this problem like for this part, you will get 5 points for this, 5 points for this, 4 points for this, 4 points, and 3 points for this question. Okay, so this is how the distribution of the work. So this problem is a comprehensive problem what you have learned in the electrostatics. So electrostatics, you draw first the electric field vectors, then you calculate the total electric field. Total electric field is the sum of x plus y components. Then you will get the magnitude of it, ex squared, ey squared. Then the direction, tangent of inverse, ey, ex. Then you calculate the force on the charge. This is the total electric field, which you have calculated like this. Then the potential, and the potential is also V1 plus V2 plus V3, and then finally we will get the work done or the potential energy stored in the charge to bring a charge from infinity to that particular point. Okay, so this is a comprehensive problem that can solve everything for the electrostatics. So this is how it works. Next, move it to the problem 3. So the next problem is a negative charge Q, 5 nanocoulomb, 5 nanocoulomb is at the center of the two concentric spherical shell. Two concentric spherical shell. This concentric spherical shell. This is a shell and this is a shell. The first spherical shell has an inner radius A. So if you see this, this is A. Okay. So this is A. And the outer radius is B. This is B, outer radius, which is this. And it's made up of non-conductive material. Non-conductive. So it cannot conduct. And uniformly charged, this is another information. which is uniformly charged in its volume with the total positive charge Q1. So it has a total positive charge Q1, which is uniformly distributed over its surface. Then you have the second spherical shell, which has a distance C and outer distance D, and it is made up of a conductive material. So it's a conductive and has a total negative charge of -7. So use the Gauss law. Gauss law. Use the Gauss law to calculate the magnitude and direction of the electric field. So to calculate the magnitude of the electric field, we have to apply the Gauss law. So Gauss law will give you the answer. So what is Gauss law? Gauss law says that the total flux through any closed surface with having a surface area is nothing but charge enclosed divided by the epsilon naught, which is the relative permittivity of free space.
Doctor,
Yeah.
can you please explain the difference between conductive and non-conductive and how we would be approach the question?
Okay. So conductive means if you have a conductor, the charge is uniformly distributed on it, and inside the hollow sphere, there is no, all the charge reside on the surface. All the charge is there. Conductive means it can conduct electricity, and if it is not a conductive, it cannot conduct electricity. Okay, so for a metal surface, all the charge reside on its surface. Inside, if it is hollow, there is no charge, no field of this. And outside, it looks like a point charge, so we can have an electric field like for a point charge. If we are far away, of if we are seeing from here of this sphere, it looks like a small point charge. So all the charge distributed uniformly on this surface, uniformly. And if we are seeing from here, it looks like a point charge. Conductive means it can conduct electricity, and non-conductive means it cannot conduct electricity as insulator material, like a plastic, rubber, or any material that you have. Now, the Gauss law. So for a Gauss law, we have to take a spherical surface which is enclosed by the which is enclosed the charge. So okay, so now we're going to apply the Gauss law on the surface to calculate the electric field and its electric field direction, in which direction it is pointed out. Okay, so for point A, so for if point A, so first we are considering point A. So at this point, we're going to calculate the electric field. So we apply this for this. For example, first we calculate the total electric field. So total electric field is for a closed surface S, we're going to calculate, which is E dot dA. So E dA, E dA is equals to closed surface EA dA cosine of theta, and because the electric field is constant and the cosine of theta is maximum, we can take it as 0. So we will get E dA. So this is a closed surface. So closed surface. So total closed surface. So the closed surface, the area of a closed surface is the integral is nothing but 4 pi r squared. So this is the electric field of a closed surface. For example, a closed surface, take it and take a distance r, okay, from any side, you get an electric field. So this is a closed surface. So, and it is equivalent to Q inside divided by the epsilon naught. So what is the electric field now? We have E is equals to 1 over 4 pi epsilon naught Q inside divided by epsilon divided by r square. So we divide over here this thing and you will get electric field. So this is the electric field, total electric field, and Q inside has this. Okay. Now if I ask you, so this is the total electric field. Now point A located at a distance RA from the charge Q. So this distance is 3.0 centimeter. So what is the electric field? Electric field at this point. So we then take a Gaussian surface around it, and then we will apply the Gauss law as well. So what is this is the electric field we have calculated. If we had at point A, we put the value of R at point A. If we have point B, then we put the value of R at point B. And if we have any other point, then we can calculate the electric field at any point inside or outside the sphere. So this is the electric field expression we have. So now what is the electric field at point A? So point A located at a distance from the charge Q. So we have electric field K Q in divided by R A squared, which is K, which is 1 over 4 pi epsilon naught. Okay, so 9 into 10 to the power 9. What is Q inside it? So Q inside is this negative Q. So the surface enclosed by this charge. So this is this value. So we have negative 5 into 10 to the power 9, negative 9 divided by R. R is this distance. So RA, which is nothing but 3 into 10 to the power negative 2 whole square, which is centimeter. So when we calculate this field, so electric field will be 5 into 10 to the power 4 Newton per coulomb. So this is the electric field at a point A due to charge Q. Okay. So if you see, this is a negative charge. So electric field should be inward. So the magnitude of E, the magnitude of E is 5 into 10 to the power 4 Newton per coulomb. And the direction, is inward. And the direction is inward.
Excuse me, doctor.
Yeah.
Doctor, for the QN, is it required just at the location A or the total QN?
QN?
Yes,
this?
when you down.
Okay,
When you write
for
negative,
this Q?
yes.
Yeah, We are talking about this charge Q, and
Okay.
it's all about this charge.
Okay. Isn't it plus 12?
No. This charge is Q, which is -5.
Okay. Okay. Thank you very much.
Okay. Let me erase this. Okay. Okay. So the electric field at this point is in this inward direction, and it has a magnitude, this value. Okay. Similarly, at point B located at a distance RB from the charge Q, same goes to E K Q in over RB square. So where is point B? So this is the point B. Okay. So this is the point B. We're going to take it the electric field. Now, if you see this at point B, this is containing this charge and this charge as well. So the total charge Q enclosed will be small charge Q plus Q1. Are you getting my point? The total charge at this point and the Gaussian surface enclosing it, this charge and this charge. Okay, and it is a distance RB, sorry, RB from the center of the point. So we will calculate, this is your EA, and this is your EB. So EB is K Q plus Q1 over RB squared. So when we substitute the value EB, we have charge Q, which is -5 nanocoulomb, and Q1, we have 12 nanocoulomb, and we substitute the value over here, we will get 1.75 10 to the 4 Newton per coulomb. Okay. So now, what is the direction of the
Doctor,
electric field? Yeah.
why point A no zero?
Sorry.
Point A, why it's not equal 0?
White at point A is not 0?
Yes.
And okay. So, because at this point A, if you draw a Gaussian surface, a closed Gaussian surface, it contains this charge. Okay. So this negative charge having the electric field inward. So this Gaussian surface contain a charge. That's why its electric field is not 0. Its electric field has to be this Q in, which is Q in is this charge. And this has a value which is -5. So if you consider at point B, so this Gaussian surface contain Q1 and this Q as well. So we have sum it up over here. Okay.
Okay, doctor, thank you.
Okay. Then at point C, so you draw a Gaussian surface over here, point C. Now this C contain this charge Q2, this charge Q1, and this charge Q. So your electric field, EC will be K Q plus Q1 plus Q2 over R square. So if you see Q is -5, Q1 is 12, and Q3 is -7. So -7 and -7, -5, 12, and 12 will give you -5, 10 raised to power -9, plus 12 into 10 raised to power 9, and -7, 10 raised to power 9, over RC. RC is 9 into 10 raised to power -2 squared, and K is nothing but 9 into 10 raised to power 9. So if you add these values, it will give you EC is 0. So your electric field is 0 at point C. It will cancel out. Okay. Now the B part. What is the total charge inner of the inner surface of the conducting sphere? What is the total charge of the inner surface of conducting sphere?
Excuse me, doctor.
Yeah.
For question A, all points are inward, right? The direction?
Yeah.
Okay. Thank you.
Because no. For point A, the direction is inward. Yeah. For point B, the direction is outward. For this, because
Positive?
for this, yeah, for this,
Oh.
this is the direction. Because at that point A, let me raise this to get you a good idea. So this is a negative charge and the Gaussian surface is like this. At this point, if we want to calculate electric field, it has to be in this direction. But for point B, if you see this, this Q1 is much greater than this charge. Okay, so the direction of at this point has to be with bigger charge, Q1, which has to be outward. Okay.
So the net charge will determine the direction.
Yeah. So net
Okay.
charge
Thank you.
at this point, the electric field is 0. So electric field at this point is 0. No direction. Okay. Now we want to calculate what is the charge on this inner surface. Okay. So it contain what kind of charge? So this inner surface contain these two charges, Q and Q1. So the total charge in the inner surface is nothing but Q plus Q1. Okay. With the negative sign. So 5 negative plus 12, you will get -7 nanocoulomb. So for the inner surface, you have negative nanocoulomb charge on this surface.
Doctor,
Yeah.
I want to ask, why did we put the negative?
Which negative?
Oh, now when you were just calculating, you put negative before it.
This.
Yeah, why did you put the negative there?
So this is Q2 is negative. This Q2 is negative. So this has to be negative charge.
Okay, makes sense.
Okay. So this is your question 2. Are we running out of time? I think. Yeah. So we have last question of this midterm. So now move it fast. So if you see this type of question, you have to identify at which point you are calculating the electric field. So you apply your Gauss law. By applying a Gauss law at any point, you have to draw a Gaussian surface and calculate this area integral. This area integral for a closed surface, the surface area will always give you 4 pi r squared. That's how we calculated over here. So your total electric field when we are looking outside this point for this point or this point or this point, we are seeing a point charge, which means electric field for a point charge is nothing but 4 pi epsilon naught q in divided by r square. So this is your electric field always. Okay, now q in has to vary. At point A, q in is only q. At point B, q1, q in is q1 plus q. And at point C, it has to be q2, q1, and q. So at which point you are calculating, that's matter as well. Okay. Now, the last part of it, a ring of center O has a radius this, uniformly charged, a total positive charge. Uniformly charged is positive charge, which is 24 nanocoulomb. What is the electric potential? Electric potential. This ring is created at point P, located on the axis at x equals to 3a, which is 45 centimeter from its center. We suppose that the potential is infinite, is zero. That's the thing. So if you are seeing this ring from point here A, okay, so at this point, so you have at this point is just looking like a point charge, but this distance has to be calculated. So this is given A, this is given as 3a. So what is this distance? Like what we did in the past by making a right angle triangle. So the potential should be at k q over r, and this distance r. So this distance r is k q over r. R is nothing but 3a square plus a square. Okay, and we have given this a, which is x equals to 3a. So a is 3a is equals to 45. So a is equals to 15 centimeters. So when we substitute the values, so k is 9 into 10 to the power 9, and q is 24 into 10 to the power minus 9, and this value is 3, a is 45, a is 15 into 10 to the power minus 2 squared plus 15 into 10 to the power minus 2 squared. So we will get the potential at point P, which is 4.5 10 to the power 2 volt. Okay. Now for this question, a particle of charge Q and mass 360 306 336 10 to the power minus 15 kilogram is released from the point P. So if a mass is released at this point, the particle is restricted to move along the ring axis. Along the ring axis, this axis is move along this ring axis. What is the potential energy of this particle at point P? So potential energy is nothing but UP is Q times potential at VP. So Q is the point charge, which is this, and VP, we have calculated this VP. So we substitute the value and you will get 2.73 10 to the power minus 6 joule. Okay. So now what is next part is what is the maximum speed that the particle can reach when it moves very far away from the very far away from the ring. So when it is very far away from the ring, so its potential energy at infinity, would be zero. So the potential at infinity will be equal to potential at this, or velocity at this infinity will be equal to this. So at this point, its kinetic energy is equals to the potential energy. So its kinetic energy at this point will become the potential energy, and we have calculated this potential energy. So from here we can calculate velocity, which is nothing but up over m, and then you take the square root and you will get v is up over m square root, which is nothing but 12.3 10 raised to power 3 meter per second. So when we consider the particle moving from point P to infinity along this axis is under the effect of the electric force. So for the mechanical energy, which is the total energy, E is K plus U, which is kinetic plus potential. So at infinity, its kinetic energy is equals to the potential energy. So that's how we can find its velocity. So this is all the problems we did. So what is the conclusion of this? So the conclusion is like this. This is an exam for the electrostatics. And for the electrostatics, you have the first thing is to calculate the force, which is K Q1 Q2 over R square. Then this force is related to the field. This force is related to the field, which is Q over R. F over Q. So this electric field. For electric field, to calculate the electric field, you have to calculate the components of the electric field along the direction x and y. Then the total electric field can be calculated with Ex squared and Ey squared. The direction of the electric field will always can be calculated by this. But if you have a positive charge and a negative charge, and this is 3q and this is q negative, so the electric field direction will be outward because it follows from the magnitude of the charge. Then it moves to the potential. So electric field is related to the potential, which is nothing but the gradient of the potential, and the potential for a point charge is k q over r. So electric field of a point charge is k q over r square. So force varies as r square, electric field varies as r square, and potential varies at r. And then from the potential, you can find out the work or the potential energy, which is nothing but the potential V. And this V is nothing but V naught at this point minus V infinity, and we take this potential 0. So this is how the electrostatics work. So they are all connected to each other in that fashion. So try to identify the configuration in which direction your electric field vector pointing out, calculate Ex, Ey, then calculate electric field, potential, potential energy, and the force. This is all you have to calculate in this exam. Okay. So if you have now any question, you can ask now, and then I will stop recording it